At the start of the nuclear weapon Cold War, engineers from the US were given a mission to develop a nuclear-armed, deep-penetration supersonic strategic bomber for the United States Air Force Strategic Air Command. A bomber aircraft would be needed to deliver the various contemporary nuclear weapons under development. At the time, nuclear weapons weighed several tons, and the need to carry enough fuel to fly that payload from the continental United States to the Soviet Union demanded large bombers. They also concluded that after the release of the bombs, the aircraft would need supersonic speed to escape the critical blast radius. North American Aviation came out with an outstanding design that used compression lift. The aircraft was named it XB-70 Valkyrie. The Valkyrie was designed to be a high-altitude Mach 3 bomber with 6 engines. Harrison Storms shaped the aircraft with a canard surface and a delta wing, which was built largely of stainless steel, sandwiched honeycomb panels, and titanium. The XB-70 was designed to use supersonic technologies developed for the Mach 3 SM-64 Navajo, as well as a modified form of the Navajo's inertial guidance system. The XB-70 used compression lift, which resulted from a shock wave generated by the leading edge of the engine intake splitter below the apex of the wing. At Mach 3 cruising speed, the shock wave is bent back about 65 degrees, and the wing is superimposed on the shock system, which is a pressure 40 pounds per square foot higher under the aircraft than in front of the shock. The compression lift provided 5% of the total lift. Camber was added to the wing leading edge inboard of the folding tips to improve subsonic handling and reduce supersonic drag. The outer portions of the wings were hinged to pivot downward by 65 degrees, acting as a type of variable geometry wingtip device. This increased the aircraft's directional stability at supersonic speeds, shifted the center of pressure to a more favorable position at high speeds, and caused the shock originating at the intake splitter to reflect from the vertical tip surface, giving additional compression lift. The 6-engine Valkyrie was capable of cruising for thousands of miles at Mach 3+, while flying at 70,000 feet. At these speeds, it was expected that the B-70 would be practically immune to interceptor aircraft, the only effective weapon against bomber aircraft at the time. The bomber would spend only a brief time over a particular radar station, flying out of its range before the controllers could position their fighters in a suitable location for an interception. High speed also made the aircraft difficult to see on radar displays, and its high altitude and high speed capacity could not be matched by any contemporaneous Soviet interceptor or fighter aircraft. But the introduction of the first Soviet surface-to-air missiles in the late 1950s put the near invulnerability of the B-70 in doubt. In response, the United States Air Force began flying its missions at low level, where the missile radar's line of sight was limited by terrain. In this low-level penetration role, the B-70 offered little additional performance over the B-52 it was meant to replace, while being far more expensive with shorter range. Other alternate missions were proposed, but these were of limited scope. With the advent of intercontinental ballistic missiles during the late 1950s, manned bombers were increasingly seen as obsolete. The U.S. Air Force eventually gave up fighting for its production, and the B-70 program was cancelled in 1961. Development was then turned over to a research program to study the effects of long-duration high-speed flight. As such, 2 prototype aircraft, designated XB-70A, were built. These aircraft were used for supersonic test flights during 1964 to 1969. In 1966, one prototype crashed after colliding with a smaller aircraft while flying in close formation. The remaining Valkyrie bomber is in the National Museum of the United States Air Force near Dayton, Ohio.